Hey folks, today we'll be talking about a couple of the classic models of the atom and what reactions can happen that involve the nucleus. So for years we had a very skewed idea of what the atom looked like. The very first person to think of an atom was the Greek philosopher Democritus, and he theorized that if you take a substance and cut it in half, and then cut it in half again, then cut it in half again, and keep cutting it in half, you'll eventually run across a very small particle that couldn't be split up anymore. Later on, we had a guy named J.J. Thomson perform some experiments and realized that that little particle had some negative and positive charges to it. His model of the atom looked a lot like chocolate chip cookie dough. In this case, the doughy goo of the cookie dough would be the positive material, and the chocolate chips would represent the negative material. It wasn't until Ernest B. Rutherford came along with his gold foil experiment until we even thought about there being a centrally located mass of positive particles. Today we call this the nucleus. Inside the nucleus we have protons, which are positive, and neutrons, which are neutral. Outside of the nucleus we have these tiny negative particles that we call electrons. And according to Rutherford, those electrons were moving around very quickly and completely at random, but still outside of the nucleus. He also had theorized that this nucleus was a very small, tightly packed, very dense piece of the atom, and then the electrons were not very dense. They were spread out and they took up a whole lot of space within the atom. Rutherford had what I like to think of as the first decent model of the atom. It was the first one that we had that discussed a nucleus. Years later, scientists named Niels Bohr came along and realized that those electrons only exist at very specific levels of energy. He represented those energy levels as being circular orbits around the nucleus. And the further from the nucleus you go, the more energy you have. Bohr just took Rutherford's model and improved upon the placing of the electrons. The Bohr model is the most simple and still fairly accurate model that we have today. There are much more complex models, which are way more accurate, but for the purposes of this class, we'll just focus on the simpler and still fairly accurate model. Now, if you've ever learned anything about magnets, you should know that similar charges repel each other and opposite charges attract. So why then do the electrons not exist in the nucleus with the protons? If electrons are negative and protons are positive, shouldn't they attract each other? The answer to that question is actually fairly simple. These electrons are moving around so quickly that they don't actually have a chance to feel that attraction from the protons. So imagine that you have two magnets and they are attracted to each other. If you take them side by side and move them in closer together very slowly, you can feel that force of attraction as they get closer. However, if you take those same two magnets and move them very quickly past each other, you don't feel that force of attraction nearly as much. It's the same way that these electrons are reacting with the protons. They don't feel that force of attraction because they're moving too quickly. You might also wonder, if like charges repel each other, how do we have protons side by side within the nucleus? That answer takes a little bit more research. So the basic concept is there are four fundamental forces on Earth. In order from weakest to strongest, we have gravity, the weak force, electromagnetism, which is those attractions and repulsions based on the charge, and then we have the strong force. That strong force only works when the particles are very close together. And that force deals with particles that are even smaller than our protons and neutrons within the nucleus. Inside the protons and neutrons are things that we call quarks. When a proton and a neutron get very close together, the strong force causes a very high attraction between the quarks and the protons and the neutrons. This attraction greatly overpowers that repulsion from the positive charges. So to answer that question, why our nucleus can exist, it's because the neutrons and the protons, when close together, have a much higher attraction than the protons do a repulsion. So, with that said, what do you think is easier to do? Add a proton to a nucleus or add a neutron to a nucleus? Well, since that strong force only applies when the particles are close together, When you're adding a proton to a nucleus, that electromagnetic repulsion between the protons is much stronger than the strong force attraction between neutrons and protons, because the neutrons and protons are too far away to feel that strong force yet. However, it's much easier to put a neutron into a nucleus because it doesn't have that electromagnetic repulsion. Funny we should talk about adding neutrons to a nucleus, because that's one of the few ways we can cause a nuclear reaction, which is what we're going to talk about next. There are three types of nuclear reactions. We have nuclear fusion, where we get two small nuclei coming together, they fuse and create a larger nucleus. We have fission, which is just the opposite. A large nucleus breaks apart into two smaller nuclei. And we have radioactive decay, in which bits of a nucleus gets removed, changing the identity of the element of the atom. Nuclear fusion happens with elements that have a smaller atomic mass than iron. The most common example are two isotopes of hydrogen coming together to make an atom of helium. This is a reaction that occurs in our sun daily. It's what gives our sun so much energy that allows it to heat the Earth. The two nuclei combine together, creating a new nucleus that has close to the same amount of total neutrons and protons. Occasionally, some of the neutrons get to escape in this process, but the combination of the two nuclei coming together creates a new single element. Here we have an atom of deuterium, which is just hydrogen with an extra neutron, and we have an atom of tritium, which is hydrogen with two extra neutrons. These two atoms are going to come together, which forms a new atom with two protons and two neutrons, which is just helium. In this case, we do have an extra neutron that gets left over, and as you can see, it doesn't become a part of the new element, it just goes off on its own way. Fission reactions happen with elements whose atomic masses are greater than iron. In this case, the atom splits up, which creates two different elements. So to do this, the atom has to be shaken up and stretched, which can usually occur by shooting a neutron at it. The atom will then split into two atoms of nearly equal size, with the possibility of having a few neutrons left over. So here you can see we have an atom of uranium, and we have a neutron that's about to be accelerated. It's going to be moving at high speeds, and when it comes in and hits that nucleus, the nucleus begins to stretch and bend. And when it's stretched enough that there's enough space between the protons and neutrons that they no longer feel that strong force attracting them together, the repulsion between protons can take over and cause the whole atom to split. The end result of this reaction is having an atom of barium and an atom of krypton with a handful of extra neutrons. Lastly, we have radioactive decay. This happens to very large atoms. It's similar to fission, but instead of taking that atom and splitting into two, it takes a chunk of that atom off, making it a smaller atom, and then you get some extra pieces off to the side. There are three major types of radioactive decay, which are named for the three chunks that you can take out of the nucleus. We have alpha decay, beta decay, and gamma decay. In alpha decay, the atom loses an alpha particle, which consists of two protons and two neutrons. That's just a helium atom without any electrons. So in this case, since we lose two protons, our atomic number goes down by 2, and since we lose two protons and two neutrons, our atomic mass goes down by 4. Here you can see the alpha decay of uranium-238. This turns the uranium molecule into thorium-234 plus an alpha particle. In beta decay, an atom with too many protons or neutrons can convert one to the other. Now remember when we talked about quarks before? So a proton has certain types of quarks that make it a proton, and electrons have certain types of quarks that make it an electron, and when those types of quarks come together, you get a neutron. So, in this case, we can turn a neutron into a proton by removing those electron quarks. Or we can take a proton, add some electron quarks, and make it a neutron. The electron quarks are called beta particles. So we can have beta minus decay, in this case where carbon releases one of the electron quarks from one of its neutrons. This adds a proton, so it adds a number to our atomic number. But it doesn't change the mass, because all we did was take out an electron, and electrons don't weigh anything. So this took our carbon and turned it into nitrogen. We can also have beta plus decay, where we take, in this case, a fluorine atom, which absorbs a beta particle, or adds that electron particle to a proton, turns the proton into a neutron, which doesn't change the mass, but it does reduce the atomic number by 1, turning into oxygen. And last but not least, we have gamma decay, which is when an atom just has way too much energy and it has to get rid of some of it. In order to do that, it emits particles of light. These light particles are called photons. Atoms are continuously absorbing and emitting these photon particles. Gamma radiation is a type of radiation that we run into daily, and it has little to no effect on us. Nuclear power plants is a type of alternative energy that gives us a way to create electricity without having to burn fossil fuels. We can put uranium atoms through some of their nuclear fission reactions and then harness its energy. So when a fission reaction occurs, it gives off a whole lot of heat, and we use that heat to produce steam, which then powers a turbine engine, which creates electricity. It's the same exact setup we have for most of our electrical power plants, in that we use something that creates heat, and then we heat up water, create steam, use it to turn an engine, and then we take the electricity from that. In many cases, we use coal, oil, or wood and put them through a combustion reaction, but nuclear fission reactions don't give off any of those harmful greenhouse gases that are caused by burning fossil fuels. So, it would be considered a clean form of energy. These fission reactions do, however, create highly radioactive isotopes of uranium. If the radiation isn't properly contained, it could leak into the environment, causing a number of issues. Now, humans run into a lot of small doses of radiation. For instance, we get radiation from our x-rays, we get radiation from our phones, and most of the time our bodies can repair the damage caused by the radiation faster than the radiation causes the damage. Unfortunately, with nuclear energy, if the doses of radiation becomes too high, it'll kill our cells faster than we can repair. More so than just killing cells faster than they can repair themselves, that radiation can actually cause mutations within the DNA of the cells. These genetic mutations could cause cancer in our normal body cells, or if the mutations happen within reproductive cells of whatever organism, the offspring of that organism could have a certain amount of birth defects. It's important to consider the benefits and the risks to nuclear energy when you're deciding whether you are for or against it. To do that, you might have to do a little bit of extra research than what you've seen in this video, but it's totally up to you to decide how you feel about it.